Hi. Now we have reached the fifth chapter of our course, and that concludes image formation part, by the way. We will start the concept of early vision, where we will start examining, analyzing the images. I will first start in this week, in this videos, something called binary image analysis. This is related to obtaining an binary mask from a gray level or color image. In fact, this conversion is the first step of a representation where some of the redundancies are removed from the image. Uh, Now, about this, I'm going to talk about some geometrical and topological properties. Then I'm going to talk about the concept of connectedness, the neighborhood concept. And I'm going to explain a few binary algorithms for representing a silhouette in a more efficient way. And finally, I'm going to talk about a pre-processing stage where gray level images are used, but from the perspective of early vision, this binary silhouette analysis and the pre-processing, I just explained in the same chapter. Now let's start. I'm talking about thresholding, okay, and histogram. There is a histogram like this. It's a gray level histogram. And I make a segmentation through thresholding. I put such a, for example, threshold. And putting the threshold gives you different, okay? Therefore, like such a threshold where this is 0, this part is 1, gives you such a very beautiful silhouette. But some images where, for example, illumination is not very homogeneous, putting thresholds, global thresholds, will not do very good. If you put the threshold like 200 somewhere here, or 128 somewhere here, or about 50 somewhere here, uh, none of them will give you good results. What is a good result? Good result is obviously able to convert or segment the background from the foreground so that the silhouette of the foreground will give you some information removed from the some redundancies, and we can go and represent those kind of images in a simple way. To tell the truth, binary image analysis is just uh, a way of representation. Gray level image is too much information, okay? And what we are doing is trying to convert the image into a form where life will be much easier in terms of representing than obviously uh, classifying anything. Now, very first, let's talk about the geometrical properties. Let's assume a continuous or discrete binary image, okay? Let's assume this is the continuous part, a binary image. Foreground is 0, background is 1, this binary image. This is continuous. If it is discrete, it will be maybe, I don't know, Bij kind of. Now, the area is, since it's continuous, a double integral. Therefore, please note if you take this integral for the foreground areas when it is 1, that will be nothing but your area over here. For the other one, for the xy inside the foreground region, if you just add only those regions where here this is equal to 1, you simply sum and you find the total number of pixels in a region. The position is obtained like an expectation operation. Like if you assume this is like a PDF, okay, that's like an expectation operation, okay. Therefore, in a way, it's like a conditional expectation here. Now, this is or the first order moment according to fundamental laws of physics. This is the position. How do we obtain the center of mass of an binary image, okay? And if you just simply add the coordinates of the pixels or the horizontal and the vertical, okay, here. If you just simply add the average of these things, you will obtain the x component of the center of mass for discrete and for continuous cases. These are our very first geometrical properties. And why this is important? Because as soon as you calculate this one and that one, and as soon as you subtract them from your silhouette, all the coordinates with respect to this new coordinate system where for example, this is xy, there is a silhouette like this. If you put your coordinate system to here, x bar, y bar, like, okay, just put this to here, then every different silhouette, different parts of the image will give you nothing but the same representation. Removing the position gives you, in a way, translation invariance. Okay, therefore, if you would like to compare one silhouette with the other silhouette, subtracting the center of mass is very critical. Okay. Now, the second important concept is the orientation. Okay, therefore, orientation, I hope qualitatively everyone understands the meaning of orientation of a silhouette, orientation of an object, orientation of a ship, for example. But here, let's have a more formal definition. I'm talking finding a line, finding the line of orientation. That line will show me the direction of the ship, the direction of the silhouette, whatever, and where all the distances, if this is this line I'm talking about, all the distances, okay, all the distances, sum of square sum, in fact, sum of the squares of the distances. When you say distance, minimum distance. Therefore, they should be orthogonal, all of them. For every point, not these points, the points inside the object where you are trying to find the orientation of the object. Therefore, all these distances is minimum. If you calculate for every such line, arbitrary line, you will see that those, for example, if there are 1000 pixels here, there are 1000 distances that you have to add, square sum. But only for one line, that summation of 1000 distances from the pixels to the nearest point on the line will be minimum, and that is your orientation line. Okay, therefore, first of all, an arbitrary point on a line. Let's start with this. Therefore, this x is on the line, this point. Okay, then we have if n is your normal vector of the line. In other words, ax plus by plus c. Therefore, the numbers in front of x and y, this is the normal vector. That normal vector, which is an inner product with the x, this arbitrary thing, obviously will give you this distance. That's a distance, okay? Therefore, that h is giving you the minimum distance from the origin, okay? Please note, if this is x, and if this is the normal, therefore, if you take the inner product, you will have nothing but that distance, okay? Now, an arbitrary point on the object, okay? Therefore, this time, we are not on the line, but on the object. The name of the point is xi. Now, what is the aim? For every xi, I will find the minimum distances, those di's, and those square sum of these di's will be minimum. Let's calculate that. First things first, xi and the normal vectors gives you ri. Ri is shown as di here, but this is the same thing. This is the distance, okay? Therefore, you have to take the square first, and you have to add that. Now, the minimum distance between the points xi and the orientation line is written like this. Di, that di, okay, this is a 90 degree, and this triangle is, this is xi, okay, and that is equal to h. Now, this is ri here, okay. I think I mistakenly say this is the di, but ri is here. Therefore, this normal vector and that xi with this normal vector is giving you this ri, okay. Therefore, this is, that part is ri. The whole thing is h. If you subtract h from, if you subtract ri from h, you will obtain nothing but this distance, and that distance equal to di. And instead of ri, you simply insert this thing here, and then square sum for every I is equal to this one. Therefore, what I'm saying is I calculated nothing but di square in terms of this one and subtracting ri from it and take the square. If you do so, we were here at this point. Now, the question is, let's find h. What is h? H is a parameter of the unknown line. Therefore, h is a parameter of the unknown line, and that h is a question mark for us right now. The question is, I find the minimum, which is this j. I find the cost function, which is this j. I want this j to be minimum with respect to a line. A parameter of the line is h. Therefore, if you take the derivative of j with respect to h, you will obtain the minimum value for obtaining j to be minimum, which value satisfies this one. Therefore, if you take the derivative, this is a function of h, obviously. 2 goes down here. There will be summation di. You open like this. And since this is a summation here, I'm talking about h, and this summation will you, and h is constant, nh. There are m pixels over there. And then the other one will be h, and this will be going inside, and you will have the summation of this part, and n transpose xi. Obviously, n transpose is constant, and you obtain this thing, okay? There was 2, but 2 is not very critical. I think you will just cancel due to this equating to 0. Now, this is the relation that we obtain. And what we say is this: the h, the optimal h, the h yielding the minimum of j is satisfying this equation. If you put h on one side, everything on the other side, you will obtain nothing but this result. Okay, therefore put this one to the other side, and you will obtain nothing but 1 over n, putting this one to here, and you will obtain this result. That inner product should be equal to h. Okay, first of all, let's remember what was it. An arbitrary point on a line, arbitrary point on a line satisfies this. Now instead of x vector, I have another vector, which is equal to h. What is that? That's equal to this one. This new vector is this. What is this vector? This is our first order moment for the horizontal and the vertical component. This is a vector. There is the average of the x values. The average of the x values is nothing but your first order moment or center of mass, which means center of mass satisfies line equation, which means center of mass passes through your certainly this unknown orientation line. But maybe the line is this one, maybe this one, maybe this one, or maybe this one. We don't know the orientation, but we don't know the angle of it, but we certainly know it passes through the center of mass. Therefore, for this orientation line, the first rule is it passes through center of mass. Okay, now what we're gonna do from now then is we just shift the center of mass. For simplicity, life will be easier. Therefore, you have the data. Before finding the any orientation line, you first take their center of mass, put the new coordinate system over there, and you look for a line passing through the origin. Okay, now let's find the angle. Okay, and then let's see how we can do that. Okay, let's assume M denote a unit vector. As you can see, I put my new coordinate system. Maybe you can put it x bar or x dash y dash. Now I have this relation here. As you can see, I know that the orientation line is passing through the center of mass. Now it's the origin. I am saying that there is an unknown M vector, this vector here, okay, this vector, this unit vector, that's important. That unit vector is the unknown direction. My goal is finding M. It looks like 2 degrees of freedom, but no, it's a unit vector, single degree of freedom, which is nothing but like cos theta, sine theta vector kind of thing, okay? Now for an arbitrary vector point xi, such an xi, this is di here, okay? This is the unit vector, okay? The di is using the Pythagoras theorem, the magnitude square of this thing, xi square, di square, and which is equal to finally xi transpose m is this distance, okay? If you take the square of it, it will be nothing but the square of this distance. Therefore, this is due to, again, Pythagoras theorem, okay? And I'm just gonna write, instead of the square, I'm gonna write xi transpose m and m transpose, I'm sorry, I'm gonna write m transpose x I like here. Therefore, okay, therefore these things will come here, and m transpose and m will be left and right multiply. Now, this is only for single in I. If I just obtain the summation, sum of not di distances, sum of square of the di distances, I think. This is already squared, by the way, yeah. This is squared here. Therefore, I'm gonna just focus on only this part. And if you just sum them, you will obtain this is this part. Now, I am trying to minimize with this constraint here. This is called constraint minimization. If you look at our background notes in the optic class, you will see the concept of this Lagrange multiplier. And this constraint is added, this equality constraint is added like this term here, okay, with a parameter unknown lambda, which is the Lagrange multiplier. And you minimize not this term, but minimize these two together, okay? Because we know that it is shown that the minimum of this cost function is satisfying. Please look at the derivations in the notes. If you have problems, you might ask me, but I will just assume this is known, method of Lagrange multiplier, cost is written, constraint is written, and the Lagrange multiplier, minimization of this thing. Therefore, the term, the m term minimizes this is my vector that I'm looking for. Therefore, I just for different m is a vector, therefore I assume this is like a gradient operator here. For every component I have to do it. If you look at here, that will be 2 times xi. I'm sorry, this is with respect to m, that will be equal to 0. And here, x transpose ax If you take the gradient, if A is symmetric, this is equal to 2AX, okay? Therefore, this is a general thing. If A is symmetric matrix, this is obviously a symmetric matrix that we have. And therefore, I'm going to have nothing but this term. And that term will bring you this thing here. And this is your like A matrix here, outer product of xi's, and this M is the unknown. Here we call it X. And for taking the derivative of this thing or gradient of this thing with respect to M, there will be 2 times M vector. 2's cancel out due to this homogeneous, and you will obtain a matrix vector minus scalar vector. This is an eigenvalue problem, okay? And we obtain nothing but the direction of the we just say it like ax is equal to lambda x, okay? And the unknown m vector, okay? The unknown m vector is nothing but the eigenvector corresponding to the minimum eigenvalue. Please note, you are trying to minimize this whole thing, and you can, instead of this, you can write alpha lambda times x. If you insert these things to here, you will see that the minimization term is equal to lambda. Therefore, we are talking about the eigenvector corresponding to the minimum eigenvalue. Okay. This is the thing that we are talking about. If you insert instead of this that term, that will bring you nothing but a simple lambda, okay? And I'm trying to minimize this, therefore I have to take the, among different eigenvalues, I have to choose the smallest eigenvalue, and the corresponding eigenvector is my solution. Now, this is all about the geometrical properties. Finding the orientation line is finding the center of mass, and after finding the center of mass, you obtain the outer product of all the points here, and you sum them up. Okay, like at the end, you obtain like a 2x2 matrix, which for every value the other products are added on top of each other, and you obtain an eigenanalysis. The eigenvector is your direction of M. Okay, now for topological, these are giving you an average value, but how about the silhouettes? The masks are like different components. Like you obtain a silhouette of 3 objects separated. This kind of an area center of mass gives you nothing but an average value for center of mass. I have to divide different components. Component meaning, there is no meaning right now, component, but there should be a meaning of connectedness. Okay, therefore 2 binary cells, 2 pixels. What is the meaning of connected? In general, connected means if there is a path can be found where your b value is constant, either 1 or 0. A connected component is the maximal set of the connected points. In other words, this point and that point, there is a path where b is constant. This point and that point, there is a path is constant. And all the maximal sets, okay, where you have connected points like this, which means nothing but this object here, this is a connected component. This point and that point, whatever you do, you cannot find the path where b is constant. This is not true, okay? Therefore, these are 2 different components. You can see everything is also a connected component. Therefore, these are called connected components. Inside, when you have a binary equal to 0, we call it holes. These are our 2 holes. and one background here, okay? Therefore, two holes, one background, and two connected components. Now, in topological properties, discrete connectedness has to be defined, 4 neighbors and 8 neighbors. 4 neighbors, these are my 4 neighbors. For 8 neighbors, this is a hole, these are the contours, 8 neighbors. Okay, these are background in a way, but here these are your contours. This is 4 connected neighbor, 8 connected neighbor. And the path is a sequence of neighboring pixels. Okay, therefore, just like here, this is neighbor to this is neighbor to this is neighbor to this, and you will have this result. Okay. Now, a very important algorithm, connected component labeling, to identify, because we obtain an image, we threshold it, we obtain a mask. Maybe the mask have like multiple connected components, 1, 2, 3, 4. I have to have a representation so that inside the matrix, for example, all the pixels of this foreground is written by 1, saying that this is your first object, this is your second connected component, this is your third, and this is your fourth. Without having this, life is a little bit misleading. Now, for example, for every such image, I can find the center of mass, I can make representations. Without analyzing a connected component, analyzing a scene as different objects is meaningless. Therefore, we have to have an algorithm to obtain connected components. There are multiple options, a recursive one, while you look starting from a non-zero point here, you say you try to grow as much as you can by recursively calling the same function. As soon as you reach background zeros, you stop and you go to the next one, kind of. I'm going to talk about very quickly on sequential one. Sequential algorithm is a very simple algorithm. Uh, Now we will go a raster scan. These are my causal neighbors. And if I have this scenario, I am this point. For these points, if I have my both up north neighbor and the west neighbor are the same, I'm gonna have saying that you are the same object. Okay, if you are this is 1 and 1, you will say you are the same object. If you have this case, or if you have this case, you also still say same object. If you have your two causal neighbors on the north and the west are they are not uh, foreground, therefore this will be a new object. Okay, but there are cases when there could be some uh, ambiguity. Therefore, for example, such a case, we have this, obviously, I'm a question mark, both of them are from the same object, and therefore that's also from the same object. Also, my left neighbor, I'm going to say this is my new, therefore I'm going to write instead of this, the same object. This one, the same object. Here, a new object. This is object 111. This is, you look at it and you say you are 2. This is 2, okay? Therefore, this is like a new object. This is 4 neighborhoods by 4 connectivity here. The question is, what is the case? One of them is one object, 1, 1, 1, 1, 2, 2. Then there is a question mark. Now you cannot make an easy solution to this. You will put an equivalence table and you will say that I'm not sure whether you belong to the 1 or the 2, but you are certainly a foreground. I'm going to give you a name, but I'm not sure 1 or 2. Let's postpone this. The sequential connected component analysis 2-step. In the next pass, we will give the answer. Okay, therefore, the idea is very simple. For example, you start here, you go like this. You come here, there's a first foreground object. This is empty, this is empty. Give the name 1. The next one is obviously 1. Previous west neighbor is 1. It continues like this, 1, 1, 1, 1, 1. Then you continue like this. You reach to here, you will give the name 2 because this is empty, it will be 2, 2, 2, 2, 2. But once you come here, you have to put 1 and 2 into an equivalence table. Maybe you will copy at this point the one on the left, but no, you will wait until this, because you put this to here as an equivalence table. Although you write it 2 for the first pass, the second pass will make everything clear. You come to continue like this, then your north neighbor is 1, therefore you will be 1, 1, continue like that. It's a newcomer 3, it will be 3 because these two are foregrounds. That will be 1, it continues like this. Okay, therefore, I am not going like this, but you can play with it. But at the end, when everything finishes, you simply write everything in the equivalence tables. 2 and 7 is turned out to be equivalent as well. Therefore, when everything is finishes, 1, 2, 7, whatever 1, 2, 7, they will be written. Therefore, that will be an object, for connected object. That will be your object, okay? And that will be, the whole thing is one single object, one connected component. Okay, that's the idea. I'm passing this. Let me say a few words for binary representations. Again, my aim is image, too complicated gray level, hopefully thresholding obtains a relatively simple silhouette. From the silhouette, I obtain orientation, I obtain center of mass. These are simple things making translation invariant. As you can see, orientation line is also making rotation invariant. If you make everyone's rotation orientation line is 90 degree to the north, then all the objects will look to the north with respect to their orientation angles, and then you can compare everything very easily. Now I'm going to continue with binary representations where life will be easier, representations will be making easier. Area, you can always use size filters and you can get rid of small binary pixels. These are called size filters, and these kind of representations removing unnecessary redundant small objects. Perimeter is a very important tool. Boundary following algorithms, they are very simple. You can just guess how can you write a boundary following algorithm. Another thing is compactness, the perimeter square versus the area. Circle is the most compact, 2 pi r square over pi r square, okay? Therefore, I'm talking about 4 pi, I think, huh? This is the most compact thing that you can have. Line is the least compact. The area is almost 0, okay? Therefore, compactness is a measure of object, how blobby it is or how elongated it is. That's a very simple measure. These measures can be used to discriminate anything that you like, any binary silhouette that you like. Therefore, these are just conversion of an image into a mask into a number. That number also could be circularity. That's also an interesting thing. It's a deviation from a perfect circle. This is the perfect circle. This is something that your object silhouette is. You find the center of mass. You find the center of mass. Okay, then you calculate for every point. These are your xk is the numbers that k from maybe starting from 0, it goes the whole way and come to the k minus 1. There are total k coordinates on this silhouette, on the boundary of the silhouette. And what I'm doing is this. I just take the difference between this one and the center of mass. This is center of mass. That is giving you this R, okay? And that R is obtained for every such step here, and you take the average of it. Therefore, you find an average radial distance for every boundary point, and the boundary point and the center of mass distance, okay? And you call this mean radial distance. In other words, you have an average object, and that will give you like a circle whose radius is mu r. That mu r like an average thing as here, which is giving you this information. Now, the second thing is how do you fluctuate from this radius, okay? Therefore, what are the distances? Then what you do is you subtract this r from this mu r, okay? And take the square, like a variance kind of concept. Therefore, how variation is at every point of r you have with respect to this constant mu r squared, and the ratio of you want mean radial distance to be equal to obviously something very small, okay? Therefore, you take this average, and I mean, obviously, that could be any value, but the variation, if you divide by this sigma r, that is basically preferring almost zero when there is no fluctuation, exactly fit to a circle. And therefore, if it is fluctuating too much, that will be small, okay? Therefore, C will be high or C will be low. This is a perfect circle or otherwise. Okay, this is the concept of circularity. Therefore, any silhouette can be converted into a number that will be a measure of how circular is it. And the final thing I'm gonna talk about is our invariant descriptors, which is uh, which is something very interesting, although it's beyond the scope of our course a little bit, but I would like to talk about these things. These are called Hughes moments, okay? These are very famous Hughes moments. Converting a binary silhouette into a representation where there is too much invariance. Okay, now this is your central moment of j-kth order. This is the j, this is the kth. Therefore, you subtract x from x bar, y from y bar, and you take the jth and the kth power, and you basically sum these things. This is a concept of maybe you remember these are these are the kth moment, okay, from probability theory. This is the kth moment of x random variable, and you can also have these kind of things as well. This is kth and this is amped power. These are the joint moment. And if you subtract the mean values, we call it central moments in probability theory as well. Here, the same idea. Only obviously you multiply with 1 for the foreground objects. These are foregrounds. You just calculate their central j-kth moments, denote like this. And please note this is invariant because we are subtracting x bar and y bar, center of mass. Therefore, these are translation invariant. And the zeroth moment is area, something general. This is variance, 0, 2, or 2, 0. Okay, if you put a 2 here, 0 here, that will go, that will be our variance. And there is skewness, kurtosis. There have some names like 0, 3, 0, 4, kind of. These are giving you how skew your silhouette in x direction and y direction, kind of. And the moment invariants are based on this. There is a concept of normalized. These are our PQ central moment. Once you just divide by this one, which is equal to P plus Q over 2, okay, therefore this is just like summation x minus x bar to the p, y minus y bar to the q. What I'm doing is I am also having nothing but the same thing, but I am taking the power of gamma with this order, and this is called the normalized central moments. And uh, it is shown that, not trivial, about 35-page paper, by the way. This one, only I'm showing four of them. There is additional three of them here as well. But these are called rotation scale translation invariant moments by Hugh. If you just calculate these things for these silhouettes, this is one silhouette, this is another silhouette, this is another silhouette. Original, rotated, scaled. Original is here, rotated and it's shifted in fact, and scaled, make it smaller. Look at the corresponding numbers for this. Look at the corresponding numbers for this. Due to discrete calculation, these numbers are slightly different. Theoretically, if it is continuous uh, image, these are exact equal, but if you have just by discretization effects, these are looking slightly different. But the interesting thing is, from a silhouette, whatever the orientation, position, scale is, if you calculate these four and these, I'm not even giving them very long, complicated. If you calculate these moment invariants, which are based on normalized central moments, if you calculate them, they will give you beautiful, exactly the same number, independent of the scale and rotation translation. That's a very powerful concept, okay? That concept can be used with many silhouettes to determine a star shape from another shape, kind of. Anything can be discriminated in this way. Okay, let me stop here. I'm gonna talk with the second video, and I'm gonna talk about morphology in the second part.